Okay, so if it's going to go a model, right, you can see it here, just right here. So two differential equations. One has a cubic nonlinearity, so that's a phase plane on the right. You see, right, this blue line. It's basically a steady state of the cubic, the first equation, right? And then the second line over here, it's basically it's called the slow null line of the second equation W, right? And both together, these two lines determine what the network dynamics should be. But again, this model is meant to produce, it's meant to produce action potentials like this in the Maris-Leca model or Hodgkin-Huxley type of model, something like that. Okay, so okay, so little historical comments. Okay, so no surprise. Okay, I'm looking at the textbook. If you look at my picture, then I'm going to switch to the, and I'm going to turn the camera off. So you see that this is cubic null lines. Okay, one is straightened, and the real cubic null lines that had 3 intersection points. So that was well known by Andronov and his students. So I'm holding the classical textbook, Oscillation Theory, right? The second edition. This is from, is it 59? Yeah, it's from 59. Is it? Okay, the green book that you see here in the slide. Okay, let me turn the camera off so I don't have to switch back and forth. Okay, so that's a later edition. So the very first edition was published in 1937, which was not a very happy year in the history of the country. Okay, and the middle author, Wheat, who was a super talented, right? He was arrested, and then he died in a gulag, and nobody knows why and how. And when the book got published for the first time in 1937, right, the title includes only 2 authors. Andronov, who's a super famous in Nizhny Novgorod, right, and he's famous everywhere. Okay, and Hiking, he's a physicist, a radiophysicist from Moscow. To me, it's a big surprise how these 3 authors put together such a fantastic book, right? And again, let me see how many pages. So this edition, it was extended by Zhelestsov, who was a student of Andronov. It includes 900 pages. The original book, I'm just curious if I have it in my office. I should have. Maybe it's in the lab. I think it's like 600 pages only. Okay, the bottom line is, of course, bottom line is that Andronov knew how to generate oscillations, right? Because he basically created what's called Andronov bifurcation that describes how these slowly converging oscillations to the steady state transforms into a limit cycle that corresponds to self-sustained oscillations in a system in a plane. Okay, so no surprise. It's again a historical comment that the book was not freely available in the West. So no surprise that Richard Fitzhugh or Naguma, who is from Japan, knew about these relaxation oscillators. So basically, they reinvented the wheel much later when they come up with this cubic null line equation, right? And simple linear equation for the what's called recovery variable. Okay, the recovery variable is supposed to give you this part in oscillations, right? And then fast spiking due to cubic null line. Okay, and basically this relaxation oscillator, that's how we used to call it, or Fitzhugh-Naguma model is a phenomenological model. Phenomenological model means that it doesn't have any exact equation, it doesn't have any specific current. It has particular features that are needed to produce spikes in the Hodgkin-Huxley type of model, okay, or in Maris-Leca. Unlike Hodgkin-Huxley original 4 differential equations, Maris-Leca only has 2 equations in it, right? And it includes, again, Lie current and then fast potassium and fast calcium currents that are in charge of generating this action potential. So this is due to fast calcium uprising, and this is repolarization is due to fast potassium current, and this slope is due to recovery variable. So I gave you this historical idea of what's going on. So basically, we're going to focus on this toy model and then transition from this toy model to Marie-Slica and eventually to Hodgkin-Huxley. But whatever we're going to discuss available for Fitzhugh-Nagoon model is going to be useful for our future studies. Okay, so let's start slowly, step by step. Okay, so we're going to consider what's called two-dimensional slow fast spiking systems. But first, I consider one-dimensional. As simple as that, x prime equals negative x, which is simple differential equation that give you exponential solution, right? That minus translates into e to the negative t. So given initial condition x naught, you converge to the steady state, which is x equals 0 level, which is the equilibrium state. By the way, what I didn't say, last week there was a talk by Lova Lerm, your professor, and Grisha Polatovsky, who talked about the mathematical legacy of Andronov, and they didn't even mention that textbook, right, which is a super classic in the field, right? And they should have mentioned that. Okay, but so basically all solutions converge to the steady state, right? If I don't have a minus and I have x here, then in contrast, right, I have solutions that diverge to they diverge from the steady state 0, right, and run to infinity. Okay, so and then you, instead of showing everything in time, you remove the time and you project the x-axis, right, make it horizontal axis, and 0 becomes what's called a steady state or stable attractor or a sink, and all solutions converge to this attractor. So we don't really want to know the rate of convergence, right? Otherwise, the equilibrium state in the second case is unstable, repeller, also known as the source. Okay, so in this hierarchy of complexity, you consider slightly, not differential equation of the first order, it's first order still, but you add up quadratic nonlinearity, so like this. So you have x squared plus the parameter that controls the dynamics of this equation, and it's basically normal form for the cell node bifurcation. I talked to Alexei, you're supposed to know that. And what happens here is that you want to find the equilibrium state. So you equate x prime to 0. So you solve this quadratic equation, and then you have two equilibrium state, and you see plus minus. And clearly, because of minus, they exist when epsilon is negative. So you have two branches. One branch is going to be unstable. This one's stable. I will talk about it in a second. And then both branches merge when epsilon is 0, and then you lose this equilibrium state at positive values of epsilon. This is called a cell node bifurcation. Okay, so basically this is illustration. This is bifurcation diagram. This is vector field. Okay, when epsilon is positive, you have nothing, right? This parabola doesn't intersect the x-axis, and then it touches it when epsilon is 0, and then you have two equilibrium states. Okay, and no surprise that because of the positiveness of this expression, when x is large enough, right, then everything x prime becomes positive, right, which means solutions run to infinity, or they converge, they run from negative infinity towards the origin. So you have this vector field on the x-axis, and this basically tells you that this point is going to be stable, this one is a repeller, and then you look at the graph and you observe that the slope of this parabola at the equilibrium state determines the stability, right? And if derivative right here is negative, then this point is stable. If derivative at this point is positive, this point is unstable, right? Then the test doesn't work at 0, of course, right? Because derivative is 0. Okay, but bottom line is that it's just regular cell node bifurcation, which is typical one-dimensional dynamics. But then it can be generalized for high dimensions, right? That's why it's so popular. The first primary. It's the first primary mechanism how the stable point loses stability, right? In this case, it merges with the unstable one, and then they disintegrate. And they disintegrate when parabola shifts slightly above the x-axis, right? And now you have what's called bottleneck effect. Okay, so basically, if you start over here, you quickly converge towards the origin, right? And then near the origin, x is small, epsilon is small, right? Which means x prime is small, so which means you kind of slowly drifting through this neighborhood, right? And then you speed up to run to infinity, right? Without any bounds. And to figure out how this time scaling work, right? You just solve this differential equation. It's separable, right? And then all x's go on the left, time goes on the right, you integrate. Okay, you just call this dwelling time. I mean, you should solve boundary value problem. But bottom line on the left-hand side, you're going to get arc10 because you have this thing, epsilon plus x squared. And then you have a factor 1 over square root of epsilon. Arc10 is known to be bounded between negative pi and power 2. So which means in the limit as epsilon tends to 0, right, over here, then the dwelling time to the bottleneck effect is determined by 1 over square root of epsilon. So it's a big thing. It allows you basically to fade. If you have a multi-dimensional system and you do know that you have a bottleneck effect and you can feed it, and if you show that the feed is going to give you a 1 over square root, you would say, this is cell node bifurcation. But of course you can determine this differently as well, right? So that basically shows how tau, the dwelling time, depends on epsilon, right? Asymptotic increase, right? Like that. In hermaphroditic bifurcation, it's different, right? It's going to be a negative log. Okay, we'll talk about this later. Okay, but now we're going back to the relaxation oscillator. Let me call it Fitzhugh-Nagumo. I mean, just don't call me non-patriotic, but it's just easier to say Fitzhugh-Nagumo because you have to deal with people you communicate, right, in neuroscience. Okay, so next we consider this equation, okay, which is basically cubic, and cubic is going to give you this profile, this graph. So therefore you have 3 equilibrium states, 0, -1, and +1. Okay, slope here is negative, which means this point is stable, unstable, unstable, right? And because you do neuroscience, instead of x, you would say V, which stands for the voltage, right? And then you add up external current, right? And that external current basically shifts this cubic null line up. So which means if it shifts up, there's 2 points, they get closer, then they merge, and then they disappear, and then you have only one equilibrium state. So you have a bistable system, 1 and 2, and now you have monostable system, okay? Or vice versa, if you shift it down by adding negative current, right, then you're going to get the same picture over here, right? So you have just one equilibrium state. And the reason I said we need 2 states, because if you remember, I mentioned when run simulations of the Hodgkin-Huxley model, then at different currents you have different states, right? One at the level of -65, which is called hyperpolarized, and if you apply positive current, then the level of the equilibrium state shifts to +40, right? So basically, this is why we use this concept, right? We need bistability to mimic realistically or phenomenologically what the Hodgkin-Huxley model has to offer. Okay, and then what we're going to do next is we're going to add up the recovery variable. Okay, we just added so with the minus in the first equation, and then we need to find out how adding the second variable affects the overall dynamics of the system. But the reason why it's called slow fast, because we need to slow recovery from, before the system generate extraction potential. That's why in the right-hand side of the second variable, W, this parameter epsilon, and epsilon is small and positive, okay, which basically makes the rate of change of W, right, it's an order of magnitude of epsilon, okay, so if f function is on the order of magnitude of 1, therefore the rate of change of W is about epsilon. In neuroscience, we don't use epsilon as a factor of the function on the right-hand side. Instead, like in case of the maximal conductance and resistance, we consider, instead of epsilon, we say 1 over tau, and tau is a characteristic time of the gate. Remember, I showed the gates that open up and close. right? And if the gate is very massive, made so of steel, right, then tau is very small, which means the gate slowly opens, right? So it's easier to talk in terms of timing rather than epsilon in a neuroscience context. So what I want to do, I want to create some kind of oscillations that look like this, right? That's why they call relaxation oscillations. So you have an on state, and then followed by recovery, and then spike, recovery. Okay, and if you make this symmetric, then recovery and spike timing is going to be basically the same, right? What do I need to do? Okay, so what I do is I always put V voltage, right, on the vertical axis, right? It's just a rule of thumbs, and the recovery variable is going to be W on the horizontal axis, and I need to arrange the following. Okay, so let's assume that my W, like the current, it shifts the cubic null line up and down. Okay, so when W is 0, right, I have by stability, and let me pick initial point up here. Okay, and the green dots just show the solutions, or I can start over here. So I converge to this stable branch, and then I need to slowly drift down, right, towards this what's called upper fold or upper knee point. Okay, and from that knee point, I fall down, land on the low branch, and then somehow I have to make sure that the vector field on this branch makes me move to the left towards this knee point. From there, I take off and then repeat the cycle of oscillation, something like this. So I need to make sure I introduce dynamics of, and I need to introduce dynamics of the W variable. So basically as simple as that. Okay, on the upper branch, W should decrease. Okay, so whenever I have equation here, on the upper branch, this function G must be negative, to make sure that, actually no, I'm lying to you. On the contrary, function G should be positive to make sure that W increases here and then decreases over here, right? And if I put things together, I'm going to get what's called the relaxation oscillator, something like that. And the simplest solution would be use this function G as just a straight line here shown in red, okay? And what it is supposed to give me is going to give me oscillation like that. So I'll show you in a second. So epsilon, okay, the equation for the W, it has epsilon, and you see it's just a straight line. Okay, shift moves this red line up and down. This red line is called as a slow null line. Null line is where W vanishes, right? And the cubic null line is called the fast null line, where V prime vanishes, right? Basically, this function F equals 0, and this function G equals 0 on this red and yellow curves, okay? And the intersection point of these lines is an equilibrium state of the full system where V prime and W equals 0, okay? So if on the upper branch over here, W prime is positive, which means G is positive. So basically above this yellow line, everything goes to the right. Then I have oscillations in the system, as simple as that, okay? So let me do this, okay? Then I'm going to show you this Java app, and okay, so Java app. That's what I said. Okay, all right. So as you can see, I have x-axis now my vertical axis, right? It's cubic null line. I have a current here, okay, and so and then some specific number, okay. I don't want to lose it, but on the other hand, okay, let's lose it. I'll just copy it, but we'll see. Okay, so all I need to get oscillations, all I need is, I want to make sure that, okay, so I have a current, let me double check, epsilon, I keep it small, in this case 0.02. Shift is just shift this red line up and down, okay. So all I need to do is, let me shift it down. I'm going to make it 0.3, okay, and I'm going to make the current 0, who cares at this point, okay. So I have no current, and I click, and you see I run the solutions, and they all converge to this fixed point. Let me increase the size of the window so you can see better, okay. So I start from here, and all points converge to the steady state. Okay, and what I can do, I click here, and it says find an equilibrium state, find equilibrium realization. I click here, and oops, no, do it again, find an equilibrium state. Click, and basically the guys who designed this Java app, they use Newton algorithm to find zeros of the function, and then what they do is, okay, you see they compute the Jacobian matrix at this equilibrium state. Okay, so f sub x, f sub y, and g sub x, and it's actually the other way around. So g first and then f, and then they compute eigenvalues, and you can see that eigenvectors. Okay, so one is negative 0.1, the other one is negative 0.2. Surprise, surprise. Okay, and clearly this guy is exponentially stable. It's stable, and then if I shift null line up, I'll just make it 0 for simplicity, right in the middle. And then if I run this, then I have oscillations in the system. So what I can do, I click here, and I want to show both x and y in time. Let me integrate it. So that's what I have, right? So this is x in time, looks like spikes. But as you can see, the recovery time and spikes are equal in size, right? Which doesn't look like real spikes, but we're gonna address this later on. Okay, and basically the reason why they're symmetric is because the red line passes through middle point of the cubic null line in the middle. Okay, so let's find the eigenvalues at the intersection point. Again, click here, say solution, find the equilibrium state. Okay, around here, it can't find it. Oh, shame on you. No, do it again. That's kind of strange. Find an equilibrium point. Okay. It can't find. All right, never mind. But bottom line is, let me just tell you, it's going to be unstable. Okay, so graph it again, and to make sure that spikes are thinner than the recovery period, all I'm going to do, I'm going to just move this red line down. Okay. Okay, so now the equilibrium state is still stable. Let me see if I can find its eigenvalues. Find the equilibrium point. Okay, let's do this. Click. Yeah, this time I'm successful. This is Jacobian, as you can see, that has complex conjugate eigenvalues. And surprise, surprise, okay, you see that epsilon is 0.02, and the real part is also 0.02. And I'm going to talk about this in a second. And let me move the null line slightly up. I'm going to make it 1.5, graph it. Okay, and now I have, looks like again, limit cycle in the plane. And I do it again, options, keep it both in time, do it again. And this time, as you can see, spikes is narrower than the recovery period. So again, qualitatively, it looks like real spikes, right? And okay, so this is called excitable media. So my cell, when I had the stable equilibrium state here, right, all solutions converge to it, right? It doesn't produce any spikes, and now it produces oscillations, okay? And if I shift this even further up, I'm going to make it, say, negative 0.15, symmetrical. Oops, sorry, negative 0.15. Graph it. No surprise that the red line moved up, okay? But still I have oscillations, and because I haven't got the stable equilibrium state yet, so I click on graph, plot this in time, do it again, okay? And as you can see, this time spike is even thicker than recovery period, okay? And it's no surprise. So basically the message that I see here is if I close it to the upper knee, the intersection, then this time is going to be longer and this is going to be shorter. And if I shift the red line down, okay, but still make sure that I don't have a stable equilibrium state here, then the recovery period is going to be longer than the spike. Okay, fair enough. Let me close this window. Okay, and if I make it like this, right? No, like 25. Do like this. Okay, then I converge to the upper equilibrium state. So back to Hodgkin-Huxley. So we have this equilibrium state when it used to be here. It's called hyperpolarized. Okay, we say this is negative 65 millivolts, right? This is plus 40 millivolts, whatever. Okay, then we have two equilibrium states depending on the current. So speaking of the current, if I make shift back to 0, right, like this, okay, and then I apply and I change this I, okay, let me just tell you, if I make it 0.1, okay, so I said positive current is going to shift this cubic nucline to the right. Okay, I'm going to make it 0.3 to shift it even further to the right. So you see now I converge to this upper steady state. So I apply positive current to make cell more excited, right? I overexcited, so everything converges to the upper state. But if I make it negative 0.3, on the contrary, it's going to shift everything to the left, which means I converge to the low equilibrium state, right? Which is hyperpolarized equilibrium state. Now I can see the connection and parallel between Hodgkin-Huxley dynamics and this Fitzhugh-Nagumo model. Okay, so I go back to make it 0 and a couple of two more experiments. All I do is I'm going to make the slope of this line. So I double the factor of y. Okay, so basically I make this line steeper. And now you see if I start over here, I converge to the upper equilibrium state. Okay, otherwise I converge to the lower equilibrium state. So my system is bistable. And this is called geometric approach, right? Epsilon is small enough to make sure that all solutions, you see, they follow the cubic nucline. Truth is that if I zoom this in, I will see that they are not on the yellow line, right? They're slightly above it, which for us means that I have a slow fast system and solutions of the system, okay, they are epsilon close to these cubic nuclines over here, okay? They are called epsilon close. So if I make this number smaller and graph it, then you basically don't see any difference, right? Because the eyeball resolution is not good enough to differentiate between the yellow line and this solution, right? But if I make it, say, 0.2 and graph it again, now you can see the difference, right? Which means this blue solution is epsilon close, but epsilon is large enough, right? So it doesn't stay close to the cubic nucline, but it follows it, okay? But it follows it. And that basically means if I go back to and remove this term, right, and run it again, then as you can see, epsilon basically let solutions run faster, which means they don't fall down immediately at the knee point. They kind of have inertia, right? But as soon as this blue solution goes underneath this red line, the vector field, right, in y pushes it to the left. You see these arrows. So therefore, it looks like moving around. But on the other hand, it's in a total agreement with this theory, right? Before, underneath the red line, you go to the left, and now you go to the right. Okay, so if I make this number something like that, you'll see how it changes the shape. Okay, but if I make it even smaller, like this, right, then you see it almost vertical fall and vertical raise on the left-hand side. This is called slow fast system. I mean, of course, if you make it unrealistically slow, right, then my software, it's called PP plane, phase plane, it has a built integration time that I don't know how to change. Say it was 100 units of time, and it moves so slowly it doesn't even complete the whole revolution because the epsilon is way too small. That's why I don't want to keep it that small, right? And I'll just increase it by 2 orders of magnitude. Okay, so I got this point, how it works, okay? On the other hand, what I can do, right, I just multiply the y variable by 0, and guess what? This null slow null it becomes just a horizontal line, okay? But it doesn't change anything. I still have oscillations. Okay, the only difference that I can see here, even at this value, there is a gap here, which means I do have some kind of inertia. Okay, but now if I want to illustrate what happens, or I want to illustrate transitions from an equilibrium state over here, if I make it 0.25 over there, I need more, say 0.5, guess what, this is 0.6, okay, so it should be at least 0.65, okay, it's just a horizontal translation down there, okay, so now you can see I converge to the steady state, I slightly move it up, okay, now I have oscillations. I want to find out what's in between. I make this number in between 55. Okay, I still have oscillations, so I need to do what I need to increase it 57. Okay, and it looks like I'm at the knee point right here. Okay, let me make it 58 over here. All right, and now apparently I have this equilibrium state. So I can, as I said, I can find the eigenvalues, but I don't want to even do that because I can clearly see that I have convergence. All I claim is that as soon as intersection, right, between the red and the yellow line is below this knee point, I have a steady state. Okay, otherwise I'm going to get oscillations. But you want to find out what's going on in between. So if I slowly raise it 575, okay, then I have oscillations. But by the way, you see how this blue solution bends? It kind of follows the unstable branch. Okay, so what I need to do, I want to get it back. So let me see, 57, do it again. Okay, now I can see either, what I can see with my eyes, either I'm trying to converge to the steady state, but I don't have enough time, or I have a limit cycle over here. Okay, let's try to be very careful. Okay, so I need to increase the size of the limit cycle, which means I have to make this parameter slightly smaller. Do it again. Okay, yeah, it looks like it's a limit cycle. You see, I have a small limit cycle. Let me try to see how it evolves as I change the parameter. So what do I need to do? I need to decrease it, right? Just remind me if I forgot. Decrease it. Okay, how about 6? Maybe it's way too much. Okay, click. Yeah, no, it works. Okay, if I start over here, I complete the round and then converge to the steady state. All right, 5, 5. Do it again. Oops, too much. So this is called the relaxation cycle. So the slow fast system, right, the feature of slow fast system is that you have a limit cycle that emerges through the Andronov bifurcation. We're going to talk about this. And apparently this is super critical because you can see a small limit cycle that quickly grows in size and becomes full size relaxation limit cycle. So I need to go back and, oops, 7. 7, what do I do? I forgot. 5, okay, 8, limit cycle. All right. Should I? Okay, should I increase it? Okay, I think I should increase it. All right, I got it. Okay, so I've got that one, and I need to decrease it. If I do 8 and start from the same initial condition, yeah, I have a full grown up limit cycle. So therefore, I got to be in between these values. Okay. Should I decrease it? Who's going to help me? Or increase it? 9. Okay, so yes, this. 8. Do it again. Right. As you can see how this limit cycle bends. So apparently it can bend this way, downwards or upwards. Okay, 9. Oops, I have to click this. Okay, gotcha. 9. So therefore, if I want to play the game, I have to be very accurate by adding these numbers. So the bottom line is that, okay, you have to be very careful by adding these numbers. So, or by lowering these numbers, 8, 5, do it again. Okay, you see it grows in size. And basically, if you accurately decrease this number, that limit cycle is going to grow like, it's going to grow like this, right? Okay, and these limit cycles nowadays in the slow fast system theory, they have an interesting name. They're called canards. In French, canard means a French duck. Okay, so and that limit cycle will follow this bullet shape of this cubic nucline. It's going to grow in size like this, right? And it can increase to a maximal canards up here, right? And then after that, as soon as I make this number smaller just a little bit, okay, no, smaller to, oh, larger, I forgot already. 8, I already lost. Okay, 9, nah, shame on you. Okay, I need to decrease it. So if I do 8, that's kind of strange. Okay, 5. Okay, how about 3? Graph it. Oops. Okay, the last one is 4. Okay, it increases very rapidly, right? It becomes full-grown limit cycle. So this is a very special case of the Andronov bifurcation, known as a degenerate Andronov bifurcation, because it changes very rapidly. But if I use, okay, so no surprise that if I add up this current and make it 0.1, because of this horizontal line, it's going to just shift the cubic nuclide left and right, but it doesn't change anything at all. So that's why realistically, I want to make sure that slow nucline is it has a certain slope. Then I go back to my lectures. So I showed you how it works. Okay, so we talked about bistability, right? If you make the slope too steep, then you're going to get 3 equilibrium state right in the middle here, unstable, and then 2 stable equilibrium state. By adding a negative current, you're going to shift the cubic nucline on the left, which means these 2 points, they will merge through the cell node and disappear, and vice versa. If you shift it to the right, then you're going to lose this stable fixed point. Okay, so that's the whole idea why either, right? Again, from mathematical perspective, I would rather use that shift parameter that shifts the red slow nuclide up and down, but in neuroscience context, my only realistic bifurcation parameter is external current or synaptic current. So that's why I shouldn't change the position of the red line and change this structure, not the structure, dynamics of the network by shifting it left or right. As simple as that. As simple as that. Okay, so okay, that's oh, sorry. Okay, there's my friends from California woke up, and now they're starting bombing me with requests. Okay, so again, equilibrium state loses stability, and then you have oscillations. And the idea is the following, okay? So if you apply a negative pulse over here, okay, then you shift the cubic nucline on the left over here, okay, and make this equilibrium state, okay, even more stable because it moves further away from the knee point, okay, underneath the knee point. If you shift it to the right and move this equilibrium state above the knee point, you make it unstable. Okay, we're going to talk about how, and I already gave you a hint. It's going to be through Andronov bifurcation, and then you have oscillations in the system, regardless where the intersection point, whether it's in the middle or not. Okay, the intersection point determines the time you need to get through the upper state, on state, or off state. So basically, you're going to control the spike duration in a system. Okay, so all right. Okay, so this is kind of interesting. So again, this is just a neuroscience context. So imagine the situation. Imagine the situation when you have an equilibrium state up here, right? Which is, we can say, oh, that's a steady state. It's called a hyperpolarized state of the system. Okay, it's stuck there, and I want to get oscillations. What do I need to do? This geometric approach tells you that you need to make sure that intersection no longer occurs on the upper branch, but it occurs on the middle intersection branch that is corresponds to the repelling equilibrium state of the fast subsystem. So I need to shift it to the right, like it's shown here, and then I have oscillations. Okay. On the other hand, this is another interesting example. What if, okay, what if, how can I get oscillations by applying a negative pulse? Okay, and this is interesting phenomenon known in neuroscience. It's called post-inhibitory rebound. Let me just tell you, let me draw a parallel, what kind of clear to you, and I mentioned that last time. All you do, you apply a negative pulse like this to the cell, right? So its voltage goes down, and then you quickly release it from inhibition, right? And the cell should produce action potentials like this, right? So you apply a negative pulse, release it, and then it generates action potential, or it may generate a single spike like this, or it may generate even a series of action potentials. Okay, so in neuroscience field, there are multiple currents that can produce these, right? But we don't have any currents whatsoever. We have a phenomenological model. How are we going to address it? And that's why we use the geometric approach, basically, in this particular case, the fact that our system is low fast. So speaking of parallel, I already mentioned last time, imagine that when Alexei goes to the for a swim, right, on a beach in G-Moria, Gorkivskaya Moria, right, and then they play volleyball, and then they use ball as a floating device, and then if you dip in the water, right, and then you release it, that the ball is going to jump out of the water up in the air, right? That's what's called post-inhibitory rebound, and then it lands on the water, and then cell becomes quiet. This is called post-inhibitory rebound. How are we going to address that? And basically what you will see here, so let's say this is a cubic nucline, and you put an equilibrium state right over here. Okay, and then you apply a pulse, negative pulse, and basically this cubic nucline is shifted to the left. So imagine it's right here, okay, it's right here. And then that's your new equilibrium state. Okay, it's right here. So that's why you want to make sure that this line is not straight. So you can see that when you apply a pulse, the voltage becomes more hyperpolarized. So which means this point in unperturbed system is replaced by a stable equilibrium state right here. And then I quickly remove the pulse. Okay, and what's going to happen? What's going to happen if the system is low or fast? Then the vector field is almost vertical over here, which means all solutions will erect, right, will converge to the upper branch, okay, and then along the upper branch of unperturbed system, they will get back to the steady state of the equilibrium state, and it will create this what's called post-inhibitory rebound. Okay, so that's what a two-dimensional system can do compared to integrating phi. Integrating phi is unable to produce anything like that. So this is called post-inhibitory rebound, and the construction of these phenomena relies fully on the fact that you have a cubic nucline, you have this hysteresis, right, and then you shift the cubic nucline to the left, or just this cubic on the left, right? Okay, so this is called post-inhibitory rebound, and that's also what happens with the equilibrium states, right? So again, this is the case when intersection takes place, occurs quite below the knee point over here, and that's what slow fast system is going to give you. So basically, you do know that it's going to be stable equilibrium state, but you want to know what the eigenvalues are with it. Okay, so what you should do typically, right? You need to, this is your function, you compute, okay, so surprised I don't see it. You compute Jacobian, you compute the first equation, right, in x and y. This equation, I mean, this is the other way around, I'm sorry, this is first, epsilon is here, but it doesn't really matter. You compute this Jacobian, and then you compute the eigenvalues, okay? And what you should see that eigenvalues should be stable, right? Meaning that they're going to be in the left open half plane in the imaginary axis, okay? And same is true if your intersection occurs on the upper stable branch, okay? And if intersection occurs over here, that equilibrium state must be unstable. It must have two eigenvalues with real positive parts, okay? So, and what happens here clearly that you see that the intersection is unique, which means you can't lose this, the equilibrium state can lose stability through the merger with unstable branch because the intersection is unique, right? It's transverse. So which means that you lose stability, the equilibrium state loses stability after passing through the knee point. Okay, so in the imaginary axis basically means that initially you have, okay, orange dot, it stands for the eigenvalue or characteristic exponent due to the slow subsystem, that epsilon makes it closer to 0, to the origin. Okay, and this one is due to the purple system, right? And what happens is as you shift this null line up, right, or you approach the knee point, okay, so that purple negative eigenvalue, this is the real, they're both real, it approaches the orange one, and then, like quadratic equation, they become complex conjugate. First double root, they become complex conjugate, and then they cross the imaginary axis to get positive real parts to make sure that the equilibrium state right here is unstable, right, an unstable focus. And as you move it up, what's going to happen is that, again, this pair lands on the real axis, right, and then decouple. So yellow stays where it should be, close to the origin, right, and the purple, right, splits and away from the orange eigenvalue, so to speak, right. And again, this is called Andronov bifurcation. Actually, this is Andronov bifurcation because Andronov considers specifically bifurcations in a plane. Okay, and this would basically that what software illustrate. Okay, right here, you look, you click find the equilibrium state, and it tells you, oh, this is Jacobian. No surprise you have 0.02, 0.02 because you have a that's the epsilon in a slow equation. And then the eigenvalue is right here, very close to the epsilon. You see there of order of magnitude of epsilon plus imaginary part, which is quite substantial, right? And then when you cross the knee point, place the equilibrium state above it, you can see that immediately, right? They're already no longer complex conjugate, but real. But the one that is due to epsilon basically is it doubles in size, and this is due to the fast subsystem. That's what I meant. How I told you that they split. So the second eigenvalue yellow is the order magnitude of epsilon. It's the same 10 to the negative 2. So it can be smaller, but it can't be more than that. So it will never become like 0.01, 0.1, I'm sorry. It can't increase in the order of magnitude. Okay, so, all right, so then the question is, all right, what kind of Andronov bifurcation it is, right? Because there are two options. Option number one is that it's called supercritical Andronov bifurcation. In a supercritical case, what you should see is that, as we saw, there's going to be a stable limit cycle that slowly emerges from now unstable equilibrium state, it increases in size, right? And then, okay, in these cases, it become large amplitude relaxation cycle, right? But typically, it's going to be just a round limit cycle that increases in size as it should increase in size, right? This is called supercritical Andronov bifurcation, okay? And people who study slow fast system, basically Andronov bifurcation in a slow fast system, they call this solution Scanart. The reason I call this Canard, maybe I'll show you next time, right? Because it looks like a French dog, but again, you have to have an artistic imagination to see that, which is kind of strange too. But bottom line, the limit cycle, it follows this bullet shape of the cubic null line, and that's what makes it Canard. The idea is that you follow the unstable branch. This is branch stable, this is unstable, and stability of limit cycles depends on how much time you spend on a stable branch versus an unstable branch. If you spend more time on a stable branch, then overall limit cycle is going to be stable and vice versa. Okay, so, and that's basically illustration how it increases in size. I'm going to show you more simulations later on, right? And then it transitions from that state. Okay, so, okay, then these are interesting cases as well, right? So if in the cubic case, right, in the first equation, if I divide the cubic equation by 3, right, then drastically change the dynamics of, or the nature of bifurcation. It becomes what's called subcritical. So what's the deal? The deal is that before, okay, everything becomes this large amplitude stable limit cycle from nowhere, right? So no surprise why the solenoid bifurcation some people refer to as a blue sky. In English, it's called out of blue. That means from nowhere, from density of trajectories. You're going to get a limit cycle that is unstable, right? In a out, it's stable in a for the out trajectories and unstable from the inner trajectories. So everything inside that red dotted limit cycle converges to the steady state, okay, and that limit cycle quickly decouples into unstable limit cycle that's about to collapse into stable equilibrium state, whereas the other one, right, will try to get the shape of the stable limit cycle like this, okay. The reason I show this loci of yellow lines showing that little variations over here, little variations, produce this unstable limit cycle, and it's quick evolution into the large limit cycle, right? So the smaller epsilon, the quicker that evolution is. So if you make epsilon, small parameter, smaller, you make the system more normal. Okay, the more normal it is, the less slow or fast it is, right? And therefore life is back to normal. Okay, so but for us, what's important is that how the bifurcation diagram is going to look like. So basically, on what you see here, this is bifurcation parameter, okay. And what I'm trying to say is that in a critical case, right, as the limit cycle increases, this is its evolution as the parameters increase. Okay, this part looks like a elliptic paraboloid, and then it quickly increases in size to become this cubic, become limit cycle due to the cubic. That's why I put this cubic line over here. It very quickly evolutions, right? So the variations on the parameter axis are very, very small. On the contrary, in a subcritical case, okay, then that surface, that elliptic paraboloid, is going to be more interesting. So the outer surface is pretty much the same, but the way it terminates through the Andronov bifurcation is different. So on that surface, there is a fold, okay, basically like a bottle of glass, right? And this corresponds to the unstable limit cycle, repelling limit cycle, ending up at the equilibrium state through the subcritical Andronov bifurcation. So it's going to look like this, right? So there's going to be a fold on that surface, okay? And interesting enough, that's exactly how it happens in a Hodgkin-Huxley model. It can be either way, depending on how you tune up some parameters of the system. So back to the Andronov bifurcation. Typically, right, when you study the Andronov bifurcation, you begin with a pendulum, conservative case, right? Harmonic oscillator, and it gives you x prime equals y prime equals negative x. The vector field is going to give you rotation. Then you introduce dissipation here, right? As epsilon negative, everything becomes the center moves into stable focus. If you make epsilon positive, therefore equilibrium state is unstable, but it's a linear system. So to get a limit cycle, you need a nonlinear term, and basically you add up this circle over here, okay, and plus minus you put, because this quantity known as Lyapunov exponent, its value, its quantity is irrelevant, but sign is what matters. So therefore you have a plus minus case, right, and you basically can normalize it by 1. And what you see here, then eventually you can get a circle of radius square root of epsilon, but it depends on a plus minus sign. So in the case when minus sign, right, which means this term is negative, right, therefore, and this is negative, you don't have a circle, so everything converges to steady state. Okay, this corresponds to the case when epsilon is 0, which means trajectory cannot reach the origin because it doesn't have a linear term that drives it towards the origin. And after that, you have a limit cycle that emerges from the equilibrium state, as I said, the radius of this limit cycle is the square root of epsilon. Whereas in a previous case, in a subcritical case, that limit cycle exists before the bifurcation. That's why it's called sub, right? And then limit cycle collapses into the equilibrium state and make it unstable. So this bifurcation diagram, basically, okay, this is a subcritical case. It shows you this elliptic paraboloid that ends up, it all originates from the bifurcation point. Okay. So now I go back to this situation, right? And I'll show you how this can be used in neuroscience context. So some particular cell, there are multiple cells in invertebrates, in non-invertebrates, and basically in sea slugs and animals that have a spinal cord. That's what invertebrates means. Then the recordings show that you have oscillations, then they decay, and then oscillations like that, kind of in the middle, and then quiescent phase. It's called elliptic burster. And then if you want to try to model the system, right, imagine the following situation. So I need, okay, this kind of construction. So you have two surfaces, outer surface that is stable, right, and the inner surface that is unstable. So it's like the case that we considered. This is subcritical Andronov-Hall bifurcation, okay, and this double limit cycle that emerges from on a fold from nowhere, okay. And what I need to do is I want to make sure that when I start, say, over here on the left, right, then my solutions kind of converge to the middle branch that is stable here. It's stable before the Andronov-Hall bifurcation. So you evolve like this, okay, and then transition, then you pass through the loss of stability, okay, over here, Andronov-Hall, right? Now you are on unstable limit cycle, say a little bit of noise, right? You lose the unstable branch, you quickly realize that you're on unstable branch, you spiral away, right, to converge to the outer green surface here. And then the vector field, in contrast, should, while you keep turning, right, it should push you on the left so that you will move towards this fold. And from that fold, you collapse back onto this line corresponding to the stable equilibrium state, and so forth and so on. How you can do that? Basically, this is, again, this is the another normal form for this double solenoid bifurcation. So basically, you have two limit cycle. Okay, one green should be unstable. That's why the sign of L2 value should be negative, and sign of L1 coefficient should be positive, right? And what is shown here, you have, so x and y is going to give you a cylindrical surface, and then you add up a z variable on a horizontal axis. And as you can see, the z dynamics is determined basically whether you're inside that tube, that cylinder, and if you happens to be inside the tube that surrounds the steady state, then the vector field z prime is going to be positive, right? Then somehow you lose its stability over here, and the radius of the tube, gray here, is smaller than the radius of the green limit cycle, which means as soon as you converge to the upper attractor, which is transient attractor, then the vector field pushes you to the left, right? And then you reach the fold, you lose the attractor, converge to equilibrium state to start another cycle of bursting. So that's basically how elliptic bursters are designed, and we're going to talk about more in the future as well. All right, how much time do I have? Somebody tell me, please. All right, it doesn't really matter.
Sure.
Okay, we have just 2 slides, and we can wrap that up after that. All right, so this is for the future, right? For the next lecture or lectures. Okay, so we'll consider some geometric configuration like that and how they shape the bursting activity in a system, right? So, and all bifurcations are going to be known for you as well, right? Again, we just talked about Andronov-Hall bifurcation, whether it's a supercritical or subcritical, how to get that fold, okay? And that's why you need equations like that, which is kind of easy to do. Then I go back to the Fitzke-Naguma. Yeah, we have 2 slides and some demonstrations as well. Okay, so the cubic null line, Okay, and again, in neuroscience, we don't say cubic here, we just say Z-shaped branch of the equilibrium state, so get used to terminology. So Z-shaped or S-shaped, if I again, flip it, it's going to be S-shaped or Z-shaped. Okay, so we need the hysteresis here, up and down, right? So these branches should overlap. And before that, the slow nucleus was just a straight line, either fully horizontal, right, or it had some slope. But this time, okay, and the reason it has to do with neuroscience as well, because I need to introduce gating variables. I already told you that gates are controlled by sigmoidal function, and sigmoidal function, it looks like this, right? This sigmoidal function, okay? And the sigmoidal function also can have a transverse intersection with the knee point, so therefore you're going to get typical Andronov-Hopf bifurcation that determines the transition from steady state, hyperpolarized steady state to the oscillations. But let me consider a very particular case when the sigmoidal function, okay, if I zoom this part in, I will see this kind of tangency. This is a cubic nuclei, and that's a sigmoidal curve, and these are tangency over here. Okay, and I'll show you how the equation looks like, or you're welcome to look something like that on the right. So the cubic nuclei, and this is sigmoidal function, and as you can see, right, as the picture on the right reveals, it looks like I start over here, looks like I have a limit cycle, but the truth is that I don't have it. All I can see is that if I start here, right, I have a single spike, and after that, everything goes to this knee point. I see little oscillations, but then everything looks like converges to the steady state, okay? And then, okay, compare this and that, you see no difference, right? 6, 8, 9, la, 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 6, 9, and then you have 2 zeros and 1, and basically this, removing these 2 zeros and 1 opens up that little gate over here, right there. So therefore, okay, this equilibrium state that used to be here, right, it merges with the unstable equilibrium state on the upper branch, right? Not this one, but locally over here. And then it opens up the passage, but due to the bottleneck effect, the time through that little gap over here is long enough. So which means, as you can see, there's a long transition from here to there, and then short spike, and then again long recovery. If again I increase the gap between nuclines, right, which means I can move faster through that region, stagnation region, then spiking becomes faster. Okay. Again, and this is, I don't want to say that one case is more realistic in neuroscience context versus the other, but it doesn't really matter. They're both typical. And the difference is that, okay, that this is called excitability 1 case. So you have an equilibrium state, and that equilibrium state loses stability through the cell node bifurcation, okay? And then you have spiking activity, and the spike period is very, very long, okay? And it's due to the bottleneck effect. As I said, that the dwelling time through the gap is proportional to its size, square root of its size, basically, which means period can be infinite. On the contrary, in the case of excitability 2, when you lose stability through the Andronov bifurcation, then the period of these oscillations, right, or period of limit cycle, is actually proportional to it's 1 over square root of the imaginary eigenvalue at the bifurcation, which means period is fixed. So that's the difference. Again, neuroscience context, they always put emphasis, right? For mathematicians, it's almost irrelevant. But in neuroscience context, the question is whether oscillations have a fixed period, finite period, or they may be made arbitrarily long. Then it's a settled mode. Okay. All right. Okay. Now, where am I? All right. And then I'm going to land up on the last slide of this lecture. And this is Maurice-Lécar neuron. So, and Maurice-Lécar is a Hodgkin-Huxley model, right? It has the Lee current, okay, like everybody else, applied current, right? And then it has, interesting, right? It has only 2 differential equations. So therefore, it has second differential equation, ECW, it's a recovery variable, Okay, so again, this is your t, which is the it's a time. Basically, it's a number 100. If I make t 100, which means epsilon is 0.01, okay, and vice versa. If I make t 1000, then epsilon is 10 to the negative 3. It's my small parameter. Okay, again, w is a probability, which means it's positive, and it should be between 0 and 1, so ignore that negative part. So basically it tells you whether the channel is open or not. If probability is 0, that means channel is closed. If probability is 1, that means channel is fully open. Okay, so that's what this curve is supposed to model. That's how the f function looks like. I'm going to talk about it later on, but I don't want to, Jesus Christ, I'm getting text messages all over the places. All right, and we're going to talk about this more in details, but okay, these are what you expect from Marie-Slick Hodgkin-Huxley type of model: recovery, fast spike, recovery, fast spike, and this is this picture. It's a MATLAB code. We're gonna run it now. This has been branded time, but most importantly, look what you see on the left hand side. Okay, you can see what looks like a cubic null climb. It's not a cubic null climb. That's what I said. It's an S-shaped curve, right? That has a hysteresis shape, overlapping parts. Okay, then this blue slow null climb for the double, right? Because of the sigmoidal function, it looks like this, right? It's a probability from 0 and then opens up all the way up to 1. In this case, cell doesn't need fully open channel, right? It kind of operates on an intermediate value, fully open, fully closed. Okay, and then there is another variable that has the same dynamics, but it's very, very fast. So again, the calcium variable here, it doesn't have any probabilities. It's either 0 or immediately 1, 0 and 1. So whether W allows you to generate spike, as you can see, it builds up, but then what's called repolarization, okay, like in the integrated phi, it basically reset. So this function over here, m, it becomes it transitions from 0 to almost 1 immediately. It's called instantaneous inactivation, right? So the pink curve must be, it should look actually like a step function, right? So that's why it doesn't have any dynamics, because it's either 0 or 1, and it doesn't take any intermediate values in between. So it's called instantaneous dynamics. Okay, so what I'm going to do next, okay, I've finished with my lectures. PDFs are there, and then I go, okay, I'll do this. I'm going to close TP plane, right, open up this file, and okay, click M files, and then I go to Fitzhugh-Nagumo, okay, and then I click that file, it's open, and what you see here, you will see Fitzhugh-Nagumo model, and what I do, I increase the current, external current, from the value of 64 up to 69, one particular range, right? Let me run it. And what you see, for each value of current, I will integrate differential equations, right, to find the solutions, and then you will see how it transitioned from a steady state here, okay? And now I shift this cubic null climb to the right, okay? So you see I converge to the steady state. I compute the eigenvalues meanwhile, and as I quickly transition, I don't see even a gap, but all I do know that eigenvalues now becomes positive. Immediately I've got very fast oscillations in the system. Okay, so that's transition from steady state to oscillations through the cell node bifurcation because of this tangency over here. Okay, now if I click at this file, it's called Fitzhugh-Nagumo supercritical hop, and then I click this. Okay, you see that this time null climb is straight line, so I have a single, it preserves stable transverse intersection. As you can see, equilibrium state gets complex eigenvalues, but still stable. Negative part is middle part still negative. Then you see more and more oscillations, right? And then, okay, it doesn't converge as fast as, but the transition is so fast I don't even see it. I don't see it, right? So it transition from small limit cycles, so there are 2 points, and then large amplitude limit cycle. If I make epsilon larger, right, I will see that it will be looking, it's going to look like a real elliptic paraboloid. Okay, so if I do it one more time, just see it for yourself. I can see the little buildup of oscillations, which tells me that eigenvalues are getting closer and closer to the imaginary axis as my amplitude of oscillations increases, right? It increases. Ideally, I should see a limit cycle, right, building up, right, and transitioning to the shape. But again, it so quickly occurs, so I don't even see it. For mathematical people, right, these transitions of that kind are very important. Now, then I click on another file that's called subhopf. And this time it's going to be very similar, but I will run two solutions, one in the forward time to get attractors and one in the backward time. Okay, so click it. Okay, so you see I converge to the steady state. And now there are two limit cycles, one stable, one unstable, red one. And that red limit cycle will try to collapse into the equilibrium state. As you can see, it's still stable. The eigenvalues have a negative real parts. Okay, still negative real parts. And that's where transition occurs. And after that, the red limit cycle collapses into this equilibrium state and make it unstable. Everything converges to the blue large amplitude limit cycle. Do it again. Okay, so you'll see, okay, how we're going to get two orbits here right now. Okay, and then they depart from each other, split. This one grows in size, this one decreases in size to collapse into the steady state and make it unstable. Okay, so that's an example of a subcritical bifurcation. But again, because we model neurodynamics, we don't want our solutions to run to infinity. So they have to be stopped by large amplitude limit cycles. So that's why we need to ensure that there are two nested limit cycles, one within another. So this, these are Fishinaguma. Then I click, go into this guy. So you need, again, make sure that you have all files, right? And I click Maurice Lecard, and this find zero little find zero. It basically, it's a Newton method to find the equilibrium state, because you need equilibrium states coordinates to compute Jacobian and then compute the characteristic exponents of the equilibrium state. So I click here, change the folder, and as you can see, okay, now maybe I was way too fast. Let me do this. Okay, this step, I'm going to make it 5, maybe even 2, so it's going to take longer, but at least I can comment on that. So that's my file. I'm going to increase it in size. So that's an equilibrium state intersection point. Everything converges to the steady state. Then it's going to become a focus, okay, and then you have a limit cycle oscillations over here. So let's do it again. Even what I'm going to do, I'm going to increase the integration time. I'm going to make it 600. Make sure that step size is smaller, and I'm going to make it, say, like this, and run it. Okay, so now you can see everything is smaller. Okay, you can, the intersection points gets closer and closer to the knee point to produce oscillations, right? Clearly, epsilon in this case is not really small. You can see the gap between Fastnall line and the solution. Right? It doesn't follow it fully. Then you see it start focusing, okay, and then it's gonna focus, right? Integrate longer, focus, and then become limit cycle. And if I keep increasing external current, then basically I'm going to shift this cubic nuclei to the right, and then I'm going to get the equilibrium state over here. Okay, so my spikes, you see how they change the shape? They're going to get thicker and thicker, and the recovery time is going to get faster and faster. But I stopped there. Okay, so let me see if I can do that with the hop, Fishinaguma supercritical hop. Let me just do this part, change the folder. Okay, I know what I'm going to change in a second. Okay, transitioning through the unramified bifurcation to get oscillations. And next, I'm going to extend the range of the current. Let me just wait. Okay, so what I'm going to do, I'm going to increase the step and hopefully, okay, I'm going to make it, I have no idea, say 158, maybe it's wrong, but let's do it again. Oh, I see it. It should be a, should be 9. Okay, do it again. All right, quickly, transition. Let me see if I was able to move the intersection point all the way up to here. No. So which basically means I need to move it up, increase it like this, and also, okay, where is the range? Plot. Okay, let's do it again. All right, transition. So you see the eigenvalues, how they split. Okay, one goes back to epsilon. I'm trying to move this point all the way up to here. Hey, can I get all the way up to here? But you'll see in a second, right? If you're going to get convergence, yeah, here we are. So then we got the intersection point, and after that, everything converges to the upper state. Very similar to what Hodgkin-Huxley neuron is supposed to do. And now you see the evolution of the eigenvalues. Okay, the left one, negative, comes closer and closer to the positive. They emerge over here, become complex conjugate. Here they cross the imaginary axis. Okay, then collapse back onto the real axis, right? And then they diverge from each other, right? And then voila. So, okay, maybe I'll just make it 1.2. You're welcome to try it, and I suggest that you download the whole directory to your laptop, and so you can play with the files and get ready for the project. At this note, right, I'm just gonna get stop here, and let me see what I need to do. I think I'm done. So I don't want to change it. I go back to 5.8 where it's supposed to be. Okay, and then I save it, and then say quit MATLAB, because I'm going to get the lecture on Saturday, so I don't quit MATLAB. I'll keep it open and close the window. All right, so at this point, I'm going to turn my camera on. All right, if I can, yeah, sure. All right. So we almost 3 hours, 2 hours 45 minutes plus the break. Any questions, guys? Any questions that you have about these topics? Hello? If you don't, huh? Hello? If you don't, then it's almost 9, right? In Russia, right? So it's kind of late, and you need your dinner and meet your friends. So at this note, I just tell you goodbye, and I'll see you on Saturday, right? At 10 a.m. my time and 6 p.m. of your time. All right. Okay. Thank you, and see you around. And please shoot me any questions and messages. Bye-bye.
Спасибо, до свидания.
Okay, thank you.
До свидания.
Thank you, bye.
Bye.
Bye.